Nuclear power currently provides 20% of the electricity produced annually in the United States. Over the next 2 decades, demand for electricity from nuclear power is expected to increase by over 13%, resulting in an increased demand for uranium, the fuel required to supply this need. Uranium is a common element found in most rocks and soil. As a result of the exposure to air and rainwater, the uranium is oxidized and becomes soluble. The uranium is then carried by groundwater through permeable rocks until reducing conditions are encountered. A reducing condition is caused by the presence of organic materials such as plant remains, coal, and petroleum hydrocarbons. In its reduced state, the uranium becomes insoluble and forms concentrated deposits often attached to the surrounding rock surfaces. Under certain conditions, uranium becomes concentrated in deposits that are economically viable for mining. One such occurrence is in the form of a uranium roll-front deposit. The uranium in this deposit often originates from volcanic materials. Over time, as groundwater continues to bring more uranium in solution, the reduction front will migrate in the direction of groundwater flow, thus creating an ore body that may extend for hundreds or thousands of feet. If a deposit is contained within a permeable material such as sand and gravel and is confined above and below by impervious shale or mudstone, it could be a potential candidate for in situ recovery or leaching, commonly referred to as ISL, also known as in situ recovery, ISR. In ISL, the leaching solution or lixiviant is usually native groundwater, enriched with oxygen and carbon dioxide. The oxygen-enriched groundwater is injected by means of injection wells into the mineralized zone and circulated through the deposit to extract the uranium. ISL mining simply reverses the natural process by oxidizing the uranium and causing it to redissolve and return to the groundwater. The uranium-enriched solution is then recovered by means of extraction or recovery wells. For ISL to be effective, the strata that host the uranium mineralization must have suitable permeability so that the fluids can be moved through the deposit. There also must be sufficient groundwater so that the pumping can be sustained for the duration of the ISL operation. Confining units above and below the deposits are typically present to control the movement of the injection fluids so that they contact the uranium ore body and do not migrate into other portions of the aquifer that are not part of the ore body. ISL is an environmentally friendly method with less impacts than open pit and underground mining methods. Surface disturbances are minimized, water use is significantly reduced, and the water quality of the mine zone is restored after mining to the target restoration goals established by the Nuclear Regulatory Commission. In addition, no tailings that must be managed are generated. ISL uranium mining is a highly regulated activity through all phases including permitting, production, aquifer restoration, and ultimately closure. These activities are regulated by several governmental agencies, including the Nuclear Regulatory Commission, the U.S. Environmental Protection Agency, and state and local environmental and public health agencies. Permitting of an ISL mine requires a thorough assessment of potential environmental impacts at all stages of the mine operation and is open to public review and comment. In order to permit and operate an ISL mine, an operator must obtain a Class 3 Underground Injection Control, or UIC permit from the U.S. EPA, or authorized state agency. A component of the Class 3 UIC permit is an aquifer exemption. It indicates that the EPA has determined the aquifer is unsuitable for use as an underground source of water for drinking, and therefore allows that portion of the aquifer to be used for ISL mining. The aquifer exemption boundary is placed outside the perimeter of the mineable ore body. In accordance with Class 3 regulations, any groundwater impacts from ISL operations must be contained within the aquifer exemption boundary. To assure that water quality impacts from ISL operations are limited to the well-filled area within the production zone, a monitor well ring is placed around the ore body but inside the aquifer exemption boundary. Monitor wells are also placed within the well-filled area in the overlying and underlying aquifers to monitor groundwater quality. To contain the lixiviant and affected mine fluids within the aquifer exemption boundary, the well field is slightly overpumped, i.e., more water is pumped out than is injected, resulting in a natural inward flow toward the recovery wells and containment of the groundwater to the immediate vicinity of the well field. This overpumpage is called bleed. A detection of impacted groundwater outside the well field in the exterior monitored wells are in the overlying and underlying monitor wells is known as an excursion. If either a horizontal or vertical excursion is detected through monitoring, the injection and extraction rates can be adjusted to hydraulically pull back the excursion before it moves outside the aquifer exemption area. Once an ore body has been determined to be suitable for ISL and permits obtained, a well field is installed with injection and extraction wells designed and constructed to isolate specific zones. A common well pattern used in ISL mining is the 5-spot pattern. This consists of a single extraction well, also called a production or recovery well, surrounded by 4 injection wells. The space between injection wells is typically between 75 to 150 feet, depending on hydraulic properties of the mineralized production zone. The well pattern repeats so that an injection well on the corner of a 5-spot pattern may supply water to as many as 4 adjacent patterns. As lixiviant moves through the production zone, the area contacted by the lixiviant increases. Over time, most of the area within the well pattern comes into contact with the lixiviant. The lixiviant chemically reacts with the rock, oxidizing, then mobilizing the uranium. The uranium-laden leach solution is captured by the production well and pumped to the surface and conveyed via pipelines to an extraction facility where the uranium is recovered. This pattern of injection and recovery continues until the lixiviant no longer contains chemically recoverable quantities of uranium. For a typical well pattern, the total volume of fluid in the pore spaces is extracted and replaced about 40 times. The potentiometric surface is reflected by the observed water levels in wells. As seen in the figure, in a confined aquifer, which is an aquifer hydraulically isolated by a low permeability layer above the mineralized zone, the potentiometric surface is usually higher than the top of the aquifer. Most ISL operations are conducted in confined aquifers, although ISL operations also have been conducted in unconfined or water table situations. This cross-section illustrates how the aquifer responds to injection and extraction during production of a well field. This illustration shows the relative magnitude of the drawdown of the potentiometric surface, or water level, around the extraction wells, and the rise of the potentiometric surface around the injection wells. The drawdown around the extraction wells and the rise of the potentiometric water levels around the injection wells develops quickly after startup of the production. As shown, steady-state conditions are rapidly achieved. The illustration shows the progression or change in potentiometric levels over time. In this example, each extraction well is being produced at a rate of 20 gallons per minute. The aggregate rate of injection in the injection wells surrounding each extraction well is slightly less than 20 GPM, resulting in a net bleed or loss of fluid. On the edges of the well field, the injection rate is reduced in this example to 5 GPM. The lower rates at the exterior injection wells ensure that the lixiviant injected in the production zone does not escape the capture zone established by the interior extraction wells. The next illustration shows a 3-dimensional view across the entire well field. In this example, the well field is relatively small, consisting of 9 extraction wells and 16 injection wells, arranged in a sequence of repeated 5-spot patterns. In this example, the total, or aggregate, extraction rate is 360 GPM, split equally among the 9 extraction wells. The injection rate in each of the interior injection wells is slightly less than 20 GPM. The injection rate in each of the irrigation wells on the corners is 5 GPM. And wells along the sides of the well field have an injection rate of 10 GPM. As shown in this view, there is a drawdown in the vicinity of the extraction well, where groundwater is moving from the aquifer into the well, and a rise in potentiometric levels around the injection well, where the water is moving from the wells into the aquifer. The lower injection rates on the perimeter of the well field result in less rise in water levels within the aquifer, allowing the extraction wells to capture all of the injected water. The hydraulic response of the aquifer occurs relatively rapidly. The previous views illustrated the response within the production zone to extraction and injection over a 2-day period. The physical movement of lixiviant through the formation is much slower. The following sequence illustrates the movement of lixiviant from the injection wells toward the extraction wells. The blue represents background groundwater conditions, i.e., not affected by lixiviant, and the red represents the presence and movement of lixiviant. In this example, it takes about 30 days for the first arrival of lixiviant at the extraction wells. We can see the lixiviant injected into the outer injection wells does not move away from the well field, but rather is kept near the well field by inward hydraulic gradient created by overpumping the extraction wells compared to the injection. The uranium-laden groundwater pumped by the extraction wells is conveyed via pipeline to a processing plant, where it is passed through an ion exchange column containing anionic resin beads that are highly selective to capture the soluble uranium ions. The uranium ion attach to the resin in a process where they displace or exchange with bicarbonate or chloride from the resin. When the resin in a column has captured a sufficient amount of uranium, the resin is transferred to a separate column and the uranium removed by an elution process using a concentrated sodium chloride solution. The uranium is then precipitated, dewatered, and dried. The uranium product, or yellow cake, is then packaged in drums for shipment to a processing facility to be concentrated and converted to a form that can be used to supply energy. The uranium-barren groundwater, leaving the ion exchange columns, is returned where oxygen and carbon dioxide are added and then re-injected back into the mineralized zone to dissolve or mine more uranium. The production cycle continues until the production fluid from each extraction well no longer contains economic quantities of uranium. At that point, the active in situ leaching operations are moved to another part of the ore deposit. When the ore deposit has been mined out, aquifer restoration begins. Aquifer restoration is the process of returning the water quality within the production or mine zone to target restoration goals set by the Nuclear Regulatory Commission. Typically, restoration includes several steps, including a groundwater sweep, groundwater treatment, recirculation, and the stabilization monitoring. The groundwater sweep is accomplished by overpumping the aquifer to pull the fluids at the edge of the well field toward its center. Groundwater treatment must commonly utilize reverse osmosis, where the affected groundwater is recovered, then filtered to remove constituents produced during the mining process. The treated water is then re-injected into the production zone. This cycle of extraction, treatment, and re-injection is repeated until the water quality within the former production zone reaches the target restoration goals determined from the pre-mining baseline monitoring. Once these goals have been met, groundwater is recirculated through the mined-out areas to ensure that the water quality is relatively consistent throughout the wellfield area and continues to meet the restoration goals. The final phase of groundwater restoration is to conduct stability monitoring to ensure that the water quality remains suitable following termination or treatment and recirculation. Once groundwater restoration has been demonstrated and approved by the regulatory agencies, the well field is decommissioned. All wells are plugged and abandoned in accordance with applicable regulations. All surface equipment, including piping and uranium processing facilities, are removed. The ground surface is regraded, reseeded, and allowed to return to its natural or pre-mining state or predetermined land use.